On the board here, I have a function y equals f of x, and I've drawn a tangent line to it called L of x. L of x is called the linearization of the function f of x, also called the standard linear approximation. Of f of x. And here I'm thinking about at the point x naught. And you actually probably studied linearizations in Calc 1, and there's even a nice formula for L of x. F of x naught plus f prime of x naught times x minus x naught. Of course, to start this, I said it was a tangent line, and that's all this is. This is the equation of a line. And if I think about it, L of x representing a y-coordinate is equal to, well, this point, I could think of that as an x naught and a y naught, plus f prime of x naught, well, that's just a slope, times x minus x naught. And this is just one little subtraction away from being the point slope form of a line. So it really is just the tangent line, right? That's all this formula ever was the equation of a tangent line. Now it's a helpful thing to recognize, and it's nice to write down, and it'll even help me spot something important in this lesson, because of course what I really want to do is think of a way to describe a surface using a linearization. And you can probably guess, but one dimension up, our linearizations won't be lines, they'll be planes. Surfaces have areas, linearizations should have areas, things that represent them. And you can probably also guess that our linearizations will just be tangent planes. So, a definition. The linearization of z equals f of xy at the point x naught, y naught is the function L of xy is equal to f of x naught, y naught plus the partial of x with respect, the partial of f with respect to x at x naught, y naught times x minus x naught plus the partial with respect to y at that same point times y minus y naught. And I'm running out of room there, but I barely got it squeezed in. All right, so that's the definition of linearization. But what this really is, well, this is taking place of a z. Plugging in an x naught and a y naught to a function gives me another z, so I could imagine calling that z naught. And then for sake of space on this side, I'm going to just write the partials, and we'll understand that we're evaluating them at that point. So I have on this side z minus z naught equals fx times x minus x naught plus fy, y minus y naught. Thinking about subtracting that over, and we're one subtraction away from having the equation of the tangent plane to that surface through that point, because this is a simple case where the partial with respect to z would be minus 1. All right, so in Calc 1, linearizations were equations of tangent lines. For us in multivariable calculus, our tangent planes are linearizations, or better said, our linearization is simply the equation of a tangent plane written down as a L of xy equals. And so this formula does become a very nice thing to know, that I have a z plus and then these two partials. So let's do an example where we write down a linearization. Find the linearization of f of xy is equal to sine of x over xy at the point pi halves comma 1 in the domain. Okay, well I have a couple choices here. I could just find the equation of a tangent plane at this point exactly the way I have in other examples, or I could use the formula for the linearization. Because this lesson is on linearizations, I'm just going to write down my final answer using this idea, but you can go about the problem however you choose. But I'm just going to evaluate the equation of the linearization and kind of do this in as few steps as possible. So I need a partial with respect to x. So I'm going to reimagine the function for a moment as z equals sine of x over x times 1 over y. Because the 1 over y is a constant if I'm taking the partial with respect to x, so I can just do the quotient rule on that bit. So the bottom gets squared, and then I have the bottom times the derivative of the top minus the top times the derivative of the bottom times that constant 1 over y. And I'm going to need to evaluate that partial derivative at the ordered pair pi halves 1. All right, so I need to plug pi halves comma 1 into this. So I have a pi halves times the cosine of pi halves. Well, nicely enough, that'll be 0 times pi halves is 0. Minus the sine of pi halves is 1. All over pi over 2 squared, so pi squared over 4 times 1 over 1. So I end up with minus 4 over pi squared. Now I need a partial with respect to y. Well, having written it down like this is still the most convenient way to do it because the sine of x over x is constant and I'm just differentiating 1 over y. And now I need to evaluate that partial at the point pi halves comma 1. And so, again, boring calculation here, I have sine of pi halves is 1 over pi halves is 2 over pi times minus 1 over 1. So I end up with a minus 2 over pi. All right, so I found my two partials. I have the ordered pair I need for here and here. I just need to find the z-coordinate that goes along with it, and I'll be able to write down my linearization. F of pi halves comma 1. Okay, so I just need to evaluate the original function at the point pi halves comma 1. On top I have sine of pi halves is 1, and on the bottom the product of pi halves and 1 is pi halves, so I end up with 2 over pi. All right, so I'm ready to go. Let me just write down some things. For the point we're worried about, the partial with respect to x is minus 4 over pi squared. The partial with respect to y is minus 2 over pi. And now the point in space I'm worried about is pi halves comma 1 comma 2 over pi, because that's my z naught. So my linearization, L of x, y, is the z-coordinate plus this partial times x minus pi halves plus this partial times y minus 1. All right, so following the equation of the linearization, that's what I get. I would encourage you to go on and distribute through this and simplify, and you'll find that your linearization is minus 4 over pi squared x minus 2 over pi y plus 6 over pi. So there's our linearization, which is really just a tangent plane solved for z. So another way through this problem would have been to find the equation of a tangent plane and just get z by itself.